You know, when most of us picture a comet, we think of a dirty snowball, right? Just a chunk of ice hurtling through space. But what if I told you that's like calling an entire city just a pile of bricks? We're going to dive deep into this, because the truth is, these celestial visitors are so much more complex and so much more important than you can possibly imagine.
So, here's how we're going to break it all down. First, we'll look at why they're like cosmic time capsules. Then, we'll dissect the anatomy of a comet, follow its wild journey around the sun, and figure out where they come from. And finally, we'll get into the really big stuff, their connection to the start of life, and the threat they pose to it.
All right, first things first, we need to completely reframe how we think about comets. These aren't just random objects floating around. They are pristine artifacts, frozen messengers from the literal dawn of our solar system.
So what does that actually mean? It means comets are our most direct link to the way things were 4.6 billion years ago. When scientists get their hands on cometary material, they're essentially analyzing a perfectly preserved sample of the original dust and gas that built everything. The sun, the Earth, all of it.
Okay, let's get a solid definition down. A comet is an icy body. Yeah, but it's a mix of frozen gases, rock, and dust. The real magic happens when it swings in close to the sun. All that solar energy causes its ices to sublimate. That means they turn directly from a solid into a gas. That process, called outgassing, is what creates all the spectacular features we're about to talk about.
So if it's way more than just a dirty snowball, what exactly is it? Let's peel back the layers and deconstruct the anatomy of one of these celestial visitors. It is way more complex than a simple ball of ice.
You see, an active comet is really a dynamic, four-part system. You've got the solid core, which we call the nucleus. As that nucleus heats up, it creates this huge, temporary atmosphere around it called the coma. And then, streaming from that coma, you get not one, but two distinct tails, the ion tail and the dust tail.
Now, this is crucial. Those two tails are completely different. The ion tail, or type I, is made of gas that's been ionized by the sun. It gets blasted straight away from the sun by the solar wind, which is why it's always perfectly straight and often has this cool blue glow. Then you have the dust tail, or type II. It's made of heavier dust particles that are pushed more gently by sunlight. This makes it lag behind, giving it that classic, curved, yellowish-white look.
And just look at the data from some well-studied comets. It shows you just how varied they are. But check out the densities. For Comet 67P, it's just 0.47 grams per cubic centimeter. That is less than half the density of water. It means that nucleus isn't a solid rock at all. It's more like a fragile clump of cosmic dust bunnies, a primordial rubble pile that's just barely holding itself together.
Now let's talk about the journey itself, because a comet's orbit isn't just a path through space. It's a powerful engine of transformation, turning a quiet, dormant chunk of ice into one of the most breathtaking sights in the entire night sky.
It's really this beautiful chain reaction. As the comet plummets inward, the sun's heat kicks off that sublimation. The gas and dust erupt outwards, forming that huge coma, which, by the way, can swell up to be bigger than Jupiter. Then, the constant, relentless pressure from sunlight and the solar wind takes all that material and sculpts it into those magnificent tails that can stretch for millions upon millions of kilometers.
But how does that sculpting actually work on a molecular level? I mean, it's so much more complicated than just a simple push. The physics at play are pretty incredible.
Okay, so let's get into the nitty-gritty. First, you have photodissociation. The sun's powerful UV light literally shatters molecules like water into their component atoms. Then comes photoionization, where that same light knocks electrons off those atoms, creating a charged gas, or a plasma. This plasma then collides with the solar wind, forming what's called an induced magnetosphere, basically a magnetic bubble that drapes around the comet. It's this whole process that perfectly funnels that charged gas straight back to form the glowing ion tail.
So, we know what they are and we know how they work, but where do they even come from? Well, to answer that, we have to take a trip way out to the most distant, frozen edges of our solar system.
You know, our understanding of this didn't just appear out of thin air. It started with Newton figuring out their orbits. For a while, people debated if they came from other stars. But the modern picture really came together in the 1950s, with Jan Oort proposing this massive, spherical cloud of comets way out there, and Gerard Kuiper suggesting another, closer disk of them. And it turns out we need both of those theories, because comets really come in two main flavors. You've got your long-period comets, which take more than 200 years to orbit the sun. They come from that distant, spherical Oort cloud, so they can pop in from basically any direction. Then you have the short-period comets. They have orbits of less than 200 years, and they come from the closer, flatter Kuiper Belt, so they tend to orbit in the same plane as the planets.
But here's the thing. These epic celestial journeys aren't forever. Every single time a comet flies by the sun, it loses a little bit of itself. Eventually, it's going to meet its end. It might just disintegrate completely, get flung out of the solar system forever by a planet's gravity, smash into something, or it could just run out of ice and become a dark, dead rock, looking just like an asteroid.
So, beyond all the cool space physics, why should we care so much about comets? Well, it's because these ancient ice balls might just hold the secret to our own existence.
I mean, the chemical richness found inside comets it's astounding. Missions like Rosetta and Stardust have confirmed they're carrying not just water ice, but crucial amino acids like glycine, the literal building blocks of proteins, and a whole cocktail of other complex organic molecules. They're like little flying chemical factories.
And all of this leads to a really powerful idea, that 4 billion years ago, during a time called the Late Heavy Bombardment, it was comets that peppered the young, sterile Earth with 2 key ingredients for life: the water that filled our oceans and the organic molecules needed to get the whole thing started.
But this cosmic delivery system, it has a dark side. The very same objects that might have brought us the incredible gift of life also happen to pose one of the greatest existential threats to it.
I want you to try and wrap your head around this number. A big comet, something like Hale-Bopp, if it hit the Earth, would release the energy of 4.4 billion megatons of TNT. That's not just a little more than the dinosaur killer. That's 44 times the energy. It's a force so unimaginable it would trigger a global extinction event that would make the last one look small.
And this really highlights the unique danger of comets. Look, asteroid impacts are way more common, for sure. But comets are a different beast. Because they fall in from the extreme outer solar system, their impact speeds are ridiculously high. We're talking over 51 kilometers per second, compared to about 15 for a typical asteroid. And since kinetic energy increases with the square of velocity, that extra speed makes comets exceptionally destructive.
Okay, let's bring it all home. Here are the 5 key takeaways. 1. Comets are pristine time capsules from the birth of our solar system. 2. They're not snowballs. They're complex systems with a nucleus, coma, and 2 totally different tails. 3. Their spectacular shows are all driven by intense interactions with the sun. 4. They come from 2 huge distant reservoirs, the Kuiper Belt and the Oort Cloud. And number 5. They represent this incredible cosmic duality. They could be the source of all life, but also a rare yet devastating threat.
And that leaves us with one last profound question to think about. When we send our spacecraft out to study these icy wanderers, yeah, we're definitely looking back in time, but maybe, just maybe, we're also looking at the very recipe that allowed us to be here in the first place, the blueprint for life, delivered from the frozen darkness of space.